So, welcome everyone. My name is Felipe and I will be your host for today's webinar on replacing your cache with ScyllaDB. In this webinar, we will deep dive on the internals of ScyllaDB's cache implementation, understand how it compares with other solutions, and walk through some successful implementations of real users who actually replaced their in-memory caches altogether with ScyllaDB. Now, for those of you who are not familiar with ScyllaDB yet, it is the database behind game changers. Organizations whose success depends upon delivering engaging experiences with impressive speed. ScyllaDB was built with a close-to-the-metal design that squeezes every possible ounce of performance out of modern infrastructure. This translates to predictable low latencies, even at high throughput. And with such consistent innovation, the adoption of our database technology has grown to over 400 key players worldwide. So, many of you will recognize some of the companies among the selection pictured here, such as Epic Games, currently using ScyllaDB to power their Unreal Engine-derived data cache. So see the cache word over here. Or Discord, who connects millions of users in real time on a daily basis. And Hulu, who use ScyllaDB for live streaming media. All right? So as it can be seen, ScyllaDB is used across many different types of industries and for entirely different types of use cases. And more than often, your company probably has a use case that is a perfect fit for ScyllaDB, but it may be that you just don't know it yet. So if you want to learn how we can help you more, feel free to engage with us. All right? So a quick intro of ourselves. I am Felipe Mendes, and I work as a solution architect here at ScyllaDB. My main role is to work closely with users during their ScyllaDB journey, gather requirements, offer consultation, and ensure that ScyllaDB is the right solution for their needs. Now, today, I am very honored to partner with a very special and dear speaker, Tomek, who is the distinguished engineer responsible for implementing the cache in ScyllaDB. So, Tomek, thank you very much for being here with us today. And could you please introduce yourself?
Yeah, my pleasure. So I am an engineer working at ScyllaDB since the beginning of the project. I'm working mainly on the replica side of things, but also other things, and I'm also a maintainer. I guess that's enough about me.
No, thank you very much, Tomek, and sorry for the slight hiccup. It was my fault. It's wrong slide driving. Yeah. So it turns out, guys, that today we have a lot to discuss. So let's do a quick run through the agenda that we've put together for today, and then jump straight right in. All right. So we are going to start from the basics and discuss why cache, so we can understand both why ScyllaDB implements its own internal cache, but really why people have a need to cache things at all, right? Next, we will quickly present real users who actually replaced their existing cache solution with ScyllaDB. And then we are going to study some of the most common caching strategies that exist. Once that's done, Tomek is going to jump in and discuss ScyllaDB cache internals. And right after, we are going to discuss some notable problems encountered when making use of an external cache, and also discuss why it might be a bad idea to do so. And finally, discuss ScyllaDB specific features to further use it as a cache replacement. All right? So at this point, you are probably wondering, what does ScyllaDB, a persistent database, have to do with caching, right? It turns out that caching happens to be a core component of ScyllaDB's architecture. If you're not familiar with the ScyllaDB architecture, ScyllaDB is built on top of a C++ framework named C star. And C star is the main component driving our shared per core and shared nothing asynchronous architecture. Now, C star provides additional benefits for real-time and latency-sensitive applications, such as a dedicated user space IO scheduler, scheduling groups for workload isolation and prioritization, and much more things. However, as you can see on the slide, there is one additional component highlighted in green, which is the subject of our talk today, our specialized cache. ScyllaDB's cache is not part of SysStar, and it was implemented to fully bypass the Linux kernel cache. And don't worry, Tomek is going to explain shortly the reasons for us to do that. All right? So, what is the problem that caches are trying to solve? Well, you have probably seen some articles such as Amazon saying that every 100 milliseconds in latency costs them 1% in sales revenue, right? Similarly, reducing average load times in your website directly correlates with less bounced sessions, which end up resulting in increased ad revenues. In the end, it turns out that a single second may simply end up costing you billions. And the longer it takes for the user to get a response, higher are the chances of increased bounce rates. Therefore, lower latencies nowadays are critical for companies to succeed and meet today's users' expectations. All right? And by the way, if you guys are currently struggling with bounce rates in your application, you may want to watch Tammy Everett's recent P99 Conf talk, where she essentially shared her insights on performance budgets for the real world. And her talk is very good, and he discussed some strategies on which you can use to tackle that kind of problem. All right? So, let's move on. What a cache tries to solve directly relates to the tail latency problem, right? That is, the fact that your user experience will be driven by the slowest 1% of your queries, which is why people care so much about the P99 these days. So, for example, if we look at the slide on the screen, we can see a very simple scenario of users interacting with an application, which then issues API calls to a backend, and those calls eventually hit the database. It all works well until you overwhelm your database. And to overcome this, most people will place a cache in front or aside their database, like this. So, while it's true that this approach typically helps reduce latencies, this also ends up elevating costs, increasing your overall application complexity, as well as introducing additional concerns that we are going to discuss later in this presentation. In summary, by doing that, you actually solved one problem, but you created another. All right? So, how can ScyllaDB help? We believe that targeting sub-millisecond latencies doesn't have to break the bank, nor have to be complex by any means. And we have several customer testimonials to further highlight this claim. So Comcast is a notable example of a customer who actually managed to not only drop their latency in 95%, and speaking of numbers, from 80 milliseconds to single-digit milliseconds on their P99.9, they also managed to reduce their previous Cassandra cluster size to only 8 nodes, resulting in 60% in TCO savings. Notably, Comcast also had a cache layer to address some of Cassandra's latency issues, which they were also able to get rid of and simplify their entire operations by going alone with ScyllaDB. So, another example I can give you is Disney Plus Hotstar. So they are another success story involving Redis as a caching layer and Elasticsearch to ScyllaDB. At this point, I know what you're thinking. So how could they switch from Elasticsearch to ScyllaDB? And it's really an interesting story, but we unfortunately don't have the time to go through it in this webinar. But you can refer to it later by following the link posted in the chat. All right. So Disney Plus Hotstar results were P99 latencies in the order of microseconds, that is below 1 millisecond, and reduced TCO, and the entire migration process from Redis and Elasticsearch to ScyllaDB was done totally online with zero downtime to their users. All right, so Grab uses ScyllaDB for real-time fraud detection, ad targeting, and as their source of truth. So their migration was a direct replacement from Redis, and then later on they introduced other use cases. And their approach similarly resulted in the very same benefits we earlier mentioned. It's actually interesting that Grab said themselves that one of the aspects that they really liked about ScyllaDB is the fact that it has the speed of Redis. So if you are interested, take the time to read their case study explaining their path and the decisions why they chose ScyllaDB. We finally get to Tubi, who started with Redis, but quickly they realized that the costs would grow too high to sustain their required traffic, and they decided to switch to Cassandra. And conversely, they realized that with Cassandra, the latency requirements wouldn't be met, which is when they engaged with us to evaluate ScyllaDB Cloud or managed service offering. So as a result of their migration, their P99s were in a single-digit millisecond, considering fault tolerance. What do I mean by that? During 2B tests, and we have worked very closely with them, we simulated several disaster situations, such as nodes going down while your live traffic is running, and observed how the system would behave during these situations. All right, so as you can see, ScyllaDB is also extremely reliable. All right, so let's now discuss some common caching strategies that exist, how they are often implemented, and some of the trade-offs to consider when using each one. Here, it's worth mentioning that different strategies other than what we are actually going to show do exist, but they're not so common, all right? So this is a chart that I stole from Byte Go, which pretty much sums it all up. So allow me to take some time here to do free advertisement for them and ask you to follow these guys, because they very often they post very interesting articles related to distributed systems design. And if you are obsessed about performance, yeah, I'm quite certain that their content will help you out. All right. So the first strategy we are going to see is cache aside, where your application looks up the cache, and in case a cache miss exists, your application will fall back to the database, retrieve the data, and update the cache. The next one is read through, where instead of your application going to the database and populating the data, the cache will automatically do it during a cache miss. Here, if we are using an external cache, we eliminate the application complexity, but the latency is still driven by the time it takes to round the trip to the external database, populate the cache, and then serve back your request. Next, we have write through, where all of your writes go to the cache, and it synchronously writes to the database. Here, your latency is driven by your database, given that your writes are pretty much synchronous, right? Down in the left, we have write around, where you write primarily to the database and read from the cache. but fall back to the database and update the cache occasionally. And finally, we have write back, where your application writes to the cache constantly, and the cache will update your database asynchronously. Here, the main drawback is the fact that a failure on your caching layer may potentially result in data loss. All right? So now, let's see how some of these implementations actually manifest themselves in practice. So for cache aside, most of the work, as we have seen, is handled by the application. Its main drawbacks are the increased complexity of handling the cache population and the fact that your latency will inevitably suffer from multiple round trips your application will have to do back and forth to keep the cache in sync, retrieve data from the database, and so on. Not to mention the fact that potential application performance/bottlenecks may further introduce additional latency to your users. All right. As an example of a write-through type of cache, we have DynamoDB Accelerator, also known as DEX, right? Which essentially sits in front of the database, and every write you perform directly to DEX is synchronized with Dynamo. One aspect that may happen when you are using this type of strategy is that if a user directly updates the underlying Dynamo table without going through the DEX endpoint, and the item in question is not yet considered stale or evicted by the cache, then reads from the cache may become inconsistent or stale. Although the general recommendation from AWS during this strategy is to prefer writing via the DEX endpoint, it happens that doing that causes writes to be more expensive, which essentially increases the overall TCO for your solution. Redis and other in-memory databases are often used as write around or write back types of strategies. And in each case, you will either sacrifice latency or data consistency. If you use write around strategy, then your application will inevitably need to do more round trips, just like in cache aside. And if you write back, an unreplicated failure may introduce data loss. All right. And finally, we get to read through, which is the strategy used by ScyllaDB. It's worth highlighting that unlike all other previous strategies that we have just discussed, ScyllaDB's cache is not an external component. Rather, it is embedded and it is shipped along with the database. All right. So I've spoken a lot. And I would like now to switch to Tomek and let him discuss ScyllaDB's cache internal. So Tomek, the audience is all yours.
Thanks, Felipe. Okay, so I'm gonna talk a little bit about the details of caching in Scylla, which are hopefully interesting to you, and demonstrate some points. In Scylla, caching is embedded, like Felipe said, and caching is done on the replica side. So you should first, to understand caching, understand how does the data flow and read flow look like on the replica side. So this is the replica side. When there is a write to the database on the replica side, it first lands into a data structure, which is called mem table, and this data structure lives in RAM. And of course, we also write it to commit block for durability, but this is not relevant for this talk. And later, when the mem table is large enough, we flash it to disk into something which is called an SS table. And later writes go to a new mem table. And after this flashing is done, the mem table is removed from the memory. And SS tables are immutable files on disk, and they form a log-structured merge tree. which is then accessed on read. When there is a read on the replica side, it has to combine data which is both in mem tables in RAM and in SS tables on disk. So an obvious way, well, actually, before I go into that, it's important to notice that with this, achieving consistency is pretty easy because you only have to ping the mem tables and the SS table set and read from that. And you have a consistent view on the state of the database. And you can do that easily because all the data structures are collocated. But it's not very efficient because read has to go to disk. So an obvious way to fix that is to insert a read through cache, which represents what is on disk, meaning SS tables. And cache is like a subset of writes which are on disk in memory. And the easiest way to implement such a read-through cache is to have a buffer cache where we cache the parts of the files which we have on disk. We cache those parts in memory. And that's, for example, how the Linux page cache works, right? You have 4 kilobyte pages, and on access to the file, if the page is not in memory, then we bring it to memory in disk. If it's in memory, then we serve from memory. And that's pretty easy. But that's not what we do, and there are several reasons why we don't do that, and you don't want to do that. One of the reasons is that it results in inefficient use of memory. If you have 4 kilobyte pages and you want to read a single row, you have to waste a lot of memory because you need the whole buffer in memory, and the row which you want to access may be just 300 bytes. That's a realistic size of a row, for example. And this results in waste if you don't have locality, and if your data set is larger than RAM, then locality is unlikely. And a similar problem exists when you try to cache in the information that there actually is no row, which is similar to the previous problem. You also need to cache the whole buffer to figure out that the row is not there. And the log structure merge tree adds another twist to that because a single read has to touch multiple SS tables. So you may have to cache multiple such buffers in order to either cache the row or the information that some SS table doesn't contain the row. The same thing, log structure merge tree also means that we have higher CPU utilization during read because you have to read from multiple SS tables. And also the SS table format is optimized for compact storage, not for read speed. So you have to spend CPU cycles for parsing the buffers. Another problem with this approach is that you can get premature cache eviction due to process which is called SS table compaction, which is something inherent to log structured merge tree. SS tables are immutable things. So after a while, we want to merge them into one bigger SS table. And that's done by the process which is called compaction. And when this compaction is finished, the old files are removed. And if you work with buffers, then you basically lose those buffers in cache. And you will hurt your performance because reads from for the keys which previously were cached will be now not cached. Sorry, the slide jumped prematurely. Yeah, so
sorry, my fault.
Yeah, I'm back in control now.
Yeah.
So there are several reasons, as you see, why using buffer cache is not optimal. So in Scilla, we don't use that. We have a different way to cache data. And we have something which is called an object cache. So the cache stores actual raw objects like mem tables, which are not associated with files on disk. They are just, you can think about them like another tree which holds the rows. And this data structure is optimized for speed of reads. It has low CPU overhead. The caching has raw granularity, so you don't cache like a bunch of rows. If you want to read a single row, you can keep only a single row in cache. And there's a single version, single copy of an object, like a row, even if it's present in multiple SS tables. So the locked structured merge tree amplification is hidden by this data structure. And we don't use Linux page cache at all in Scilla. We want to dedicate most of the memory on the node to our cache. So Scilla reserves most of the memory on the node, leaving only some small reserve for the operating system, things like socket buffers and other stuff. But most of the memory is managed inside Scilla, and most of that memory goes to the cache. And this cache grows automatically and shrinks automatically when there is internal pressure for memory from Scilla. There is another very important piece of design which is related to caching. In Scilla, we have CPU sharding, which means that data structures like cache and mem table and SS tables are split across CPUs in such a way that each CPU is responsible for only a fraction of keys. And those data structures are only accessed through that CPU. They are not shared between CPUs. And there is a one thread per CPU, which does all the execution. All execution is split into small tasks, which are executed sequentially. They exclude with each other. And the preemption is cooperative, meaning that we decide in code what are the boundaries of the tasks. And if there is a preemption signal, which comes from a timer, then the task has to yield cooperatively. It's not preempted in any place. It can decide what are possible preemption points. It's very important and useful because this means we can have very complex operations on data structures within tasks. And those operations are guaranteed to be executed in isolation, atomically. And we can have concurrency control due to this design, which means we don't have to use other mechanisms for concurrency control like locks or lock-free algorithms. Those things are not necessary. And that gives us lots of flexibility in implementing the algorithms. For example, you can have a single task which performs lookups in both the cache and mem table, and it will have a consistent view on the state of the data because it excludes with any other task. And the data structures can be simple. They don't have to be either riddled with locks or prepared for lock-free algorithms, which you would normally do in a multi-threaded environment. And one thing to note here is that this is possible also because we have collocation of cache and the replica. So everything happens within a single CPU. Otherwise, it wouldn't be possible. Yeah, there are some problems related to caching and complex operations on data. Scilla is not a simple key value store. It has some more complex operations like range scans and range deletions. And that has implications for caching. For buffer cache solution, that's maybe not a problem because whatever you read from disk, you can also read from the buffer cache. But for object storage, it has some complications. Take range scan, for example. If your cache is just a set of keys, then you don't know if between the keys there isn't some data on disk which the cache doesn't contain. So if you had a naive implementation of the cache, then such a scan would have to always go to disk to figure out if there are any keys between the keys which are in cache. And in Scylla, we take care of such operations. Our cache is prepared to efficiently handle such operations. And it does so by storing information about range continuity. So when populating the cache, we remember that the range is complete, meaning that there is no data on disk for this range. So when you have a scan, we don't have to go to disk. We know that the range is complete, not just the keys. And also deletions. Deletions have to be handled in a special care because due to eventual consistency in Scylla, deleting a range of keys is not just about dropping rows. You have to also store the information about the deletion, which is called the tombstone. That's needed for reconciliation of read results between replicas. And the cache has to also store this information appropriately to serve it to reads. And we do it by using a similar mechanism, like I mentioned before, which is range continuity. We record the information that a range in cache is complete, but also annotate it with deletion information. So this is also something which is taken care of. So to sum up, Scylla has a fast cache, which is optimized for reads. And due to collocation of data in the cache on the same CPU, it's maintained efficiently and takes care of some various intricacies related to data model and query model, and takes care of all the consistency guarantees which ScyllaDB is supposed to provide. So external cache doesn't have to deal with those. And that's all I had. Now back to Felipe.
Thanks, Tomek, and sorry about the hiccups with the slides. I was trying to mute myself. I hope I haven't ruined your brilliant presentation. I even learned a lot of stuff myself, so thank you very much. By the way, guys, there was a very good article from Tomek where he essentially explains more about the ScyllaDB's cache. So you may want to read it if you want to understand deeper on how it works. Again, Tomek, so thank you very much. So let's now switch focus to and highlight some of the problems involved when you make use of an external cache. We have listed here 7 reasons related to latencies, costs, complexity, and so on. And we will quickly walk you through these points. So it's worth noting that we have a very detailed white paper where we discuss each of these aspects in depth. So you may want to give it a read as a follow-up to this webinar. All right, so the first aspect we are going to cover refers to latency, which may seem a bit counterintuitive at first, since the overall goal of you to place a cache in front of your database is to reduce latency, but it makes sense when you stop and think about it. So inevitably, an external cache will introduce latencies, such as what we have seen during the cache aside and the write around strategies. Whenever you have a cache miss, which may happen more often than you might think, your application or cache will need to fall back to the database and this entire round trip will have a cost. Of course, you may decide not to fall back to the database, but that would mean that you would be serving either no data or stale data to your users, right? So in this slide, we have an example of an external cache with Cassandra, and versus how it would work if you are using ScyllaDB. All right. The next aspect relates to costs. So when you use an external cache, it may happen that your workload scales up to a point where your data no longer fits the previous infrastructure you originally provisioned and intended to run that workload. This is pretty common since workloads nowadays, they are not static, right? Typically, a good sign when this actually happen is when your cache misses start to get even or higher than your actual cache misses. So at some point, you will need to both scale your underlying database as well as your cache. So it's not only about the infrastructure and licensing costs that we are discussing here, but also the human efforts involved as well to keep up with the space. I mean, now you're managing two solutions other than just one. With ScyllaDB, I mean, if your workload grows and your latency starts to deviate from what you would expect, I mean, you would simply add more nodes to the cluster and you would still keep running on the very same database. That's simple. All right. The next topic is the fact that an external cache reduces your availability. And this happens due to three main aspects. First, the fact that if your external cache goes down, your application will need to handle that situation and know how to fall back to your database. Second, the fact that most of the time people rely on their cache to fulfill their SLAs. So in that sense, even if your application properly handles the failover logic, it will likely overwhelm your database, and this may result in unavailability for your end users. And finally, activities such as upgrades, node maintenance, and other routine activities may invalidate your cache and introduce other availability concerns. So, in ScyllaDB, you also need to perform maintenance operations. So you have to upgrade your cluster, do a cluster rolling restart, etc., and so on. But in ScyllaDB specifically, we implemented an optimization called heat-weighted load balancing. And what this optimization does is to actually ensure that replicas with a cold cache are favored against replicas with a cold one. This is useful in case you are upgrading your ScyllaDB cluster, because the database ensures that cold replicas will populate their cache again at a pace that doesn't harm your latencies. The next drawback of an external cache lies down on the application complexity. And really, we have discussed the additional application effort needed at several strategies early in your presentation. This includes, at times, handling failover logic, populating the cache, handling evictions properly, and most importantly, ensuring that the data you serve to your users is correct and relevant. All right. And this one is actually an interesting one. It ignores the database knowledge. So even though, the several in-memory caches can support several data types, the reality is that not always this will be compatible with your database. Take ScyllaDB UDTs as an example. How should we represent this data in an external cache? So this is yet another aspect that you will need to handle from your side. Another concern is how, for example, you would handle time to live, TTL, or other specific characteristics, such as write timestamp, which in your cache. Of course, cache supports TTL, but these are typically independent from the ones configured and persisted to your database, which means that that's yet another aspect for you to handle. All right. And of course, an external cache will inevitably ruin your own database's cache, such as ScyllaDB's cache that Tomek just explained. So database, be it either ScyllaDB or not, databases have carry on a lot of context over how you query your data, and they typically optimize themselves to your access patterns. When you use an external cache, by the time your application or the cache needs to query the database directly to retrieve this data, it's very likely that the queried item is going to be cold, effectively turning your database cache ineffective. All right? It's also worth mentioning other concerns, such as security. When you directly query your database, it will typically go through an authorization process to ensure the application is actually, and the users are actually authorized to read that data. Once you introduce an external cache, you need to also make sure you apply these security governance policies you have also there in your external cache. So to prevent, potential data breach. So you essentially double all of your infrastructure efforts. All right. Now, we finally got to the final section of our presentation where we are going to discuss ScyllaDB's cache-related features. And let's start with observability, right? So observability is crucial to any distributed system. And with ScyllaDB and its cache, it is no different. So all metrics you would expect to see are available via the ScyllaDB monitoring stack. So for example, this slide shows a monitoring snapshot I took. It was essentially a benchmark I was running. So it's not really a real production workload being depicted over here. But they do show, the relevant cache information. So we do have, cache misses, cache reads, how many rows are being hit, how many rows are being missed, which means the database needs to go to the disk. How big is, how much space is your cache currently consuming, broken down by memory size, number of partitions, number of rows, etc., and so on. And what's cooler about all those metrics is that every single metric is available per CPU or per shard in ScyllaDB's terminology, giving our shard per core architecture. That means you are able to see how each CPU in your cluster is individually performing and easily identify potential bad access patterns in your application. All right. So bypass cache. So ScyllaDB is a read-through type of cache, as Tomek explained it, which means that by default, every read you perform will be populated to the cache and then served back to the user. However, this may not be always what you want. What do I mean by that? For example, if you are potentially scanning tons of data, or occasionally you have to query data that's unlikely to be read again in the future, it may happen that those reads may invalidate important items from your existing cache. So to prevent this situation altogether, ScyllaDB extended the SQL protocol with the bypass cache extension. What it does, in simple terms, is to hint to the database that it should not populate its cache with the items it reads as a result of your query, and therefore preventing validating important records. So when, Felipe, tell me a specific use case where you see bypass cache being used. It's typically used in conjunction with workload prioritization on analytics use case, which frequently have to scan through books types of data. Typically, when you hook up Apache Spark, Presto, or some other query processing tools alongside with ScyllaDB, that's the moment when you typically want to run bypass cache. Especially if you have a real-time workload running alongside it. All right. And the next improvement that we want to highlight here for you is SS table index caching. So SS table index caching is a feature Tomac here introduced and presented in our ScyllaDB Summit. It essentially involves also caching the SS table index component to further speed up reads that have to go to disk. So the SS table index is automatically populated on access and evicted on memory pressure in such a way that it doesn't affect your workload latencies by any means. So one of the many benefits of SS table index caching is the fact that large partitions are no longer an issue in ScyllaDB. So for example, this slide shows the measurements that Tomac did and presented back then at ScyllaDB Summit before and after the optimization with large partitions, directly reading code data from disk. So as we can see, the throughput more than tripled, and which essentially made on-disk lookups even faster than before. All right. And well, this is pretty much what me and Tomac had to present. So as a summary, we have discussed the potential hiccups of placing a cache in front of your database. We understood that an external cache lacks the context your database has for your workload and may turn your database-specific optimizations inefficient. We have also seen how the ScyllaDB internal cache works and how and why multiple game changers replaced their external cache with ScyllaDB. Lastly, we walked through some optimizations and features which make our database on par, both from a performance standpoint, but also with feature parity with other competitors. All right? So this brings us to the end of our presentation. And before we jump to our Q&A section, here are some research for you to get started with ScyllaDB. First, ScyllaDB Cloud is our ScyllaDB managed solution backed up by a team of experts. Sign up at ScyllaDB.com/cloud and start a free trial. And remember, Tubi, one of the customers I presented earlier, is currently running ScyllaDB Cloud. Next, in 2 weeks from now, we'll be launching our Database Performance at Scale Masterclass. If you guys don't know what Database Performance at Scale is, it is essentially one of the books I am proud to be an author of, along with other brilliant speakers, Pavel Emelianov, Piotr Sarna, and Cynthia Dunlop. So I am personally inviting you to attend so you can learn more about all the considerations and aspects involved when optimizing database performance. So register now to get a free copy of the book and enter the drawing to win a physical copy. All right. And lastly, ScyllaDB University Live is taking place on December 5, and sign up in order to watch live sessions with instructors and have your questions answered. All right, cool. All right, with all that said, let's start our Q&A. And I can see we have a lot of questions. Awesome. Oh, that's actually a very good question. Tomac, what's ScyllaDB's cache eviction policy?
Yeah, right. So in Scylla, the primary reason to evict the data is when there is memory pressure from other things than the cache, for example, mem tables or standard allocations. And eviction happens by choosing least recently used object from the cache. So we use ALRU basically.
Least recently used, right?
Yeah, there are other occasions where objects are evicted from cache. For example, obvious example is when you drop a table, then objects are also evicted, but that's not interesting here, I guess. The main policy is salary.
So I see. Yeah, do you want to add something else?
Yeah,
Sorry.
there's also a case of TTL, because the data model allows you to insert data with TTL, meaning that it becomes deleted after a period of time. And we have it solved in our cache in the following way. Basically, once items expire, they no longer have to take space in cache, and we don't want them to take space in cache. So when you have expired data and you read them, and then they are removed during read. So we piggyback on the read process to remove expired data.
Very interesting. Very interesting. So I see two other questions here that I think I can tackle. And so the question is, can ScyllaDB cache relational database tables as well and allow GML operations? And what about join queries? So ScyllaDB is a NoSQL data store. We don't support joins nor relational types of queries. So we are a wide column database, but you can use ScyllaDB as a cache in front of your relational database. There are several customers who actually are using ScyllaDB for that, but you would need to essentially apply the very same, use ScyllaDB as an external cache to your relational database. All right. So I hope I addressed this question. Is there any other question you would like to answer live, Tomek, or otherwise I can just throw at you? I can see we have tons of questions.
I can see a question on the chat. If we can configure a cache size in such a way to grow and work with limited space. So the answer is you cannot change the space taken by cache dynamically while the server is running. You can reduce the size of the cache by giving Scylla process less memory, which you specify as a command line argument. But I wonder, why would you want to give cache less space? What would be the reason for that? Because cache gives back memory as there is demand from other things. So you cannot fail allocations just by giving cache more space.
There is one question here that is very deep into the our implementation. How do we store rows in memory? Is it a hash table or a B tree?
We use a custom implementation of a B tree to store them in memory, written by Pavel Emelianov.
One of the book authors, yeah. And by the way, Pavel Emelianov in the masterclass is going to talk about his optimizations in B trees. But sorry to interrupt, you may continue. Are you done?
Yeah.
Awesome. Thanks, Tomek. Let's see what else. Does ScyllaDB use RocksDB underneath? I don't think we do we, Tomek?
RocksDB? No.
Yeah.
We don't use it.
Our cache is our own, right? Yeah. Let's see what else. What happens to the cache when the node crash? Can you elaborate on the process of recaching? I think he refers to the hit-weighted load balancing I mentioned earlier. Do you want to hint on any ideas?
So when Scylla crashes, then the cache goes away, and when it comes back up, it has to be populated again and warmed up. And that's something which hit-weighted load balancing helps with, because if you have a single Scylla server crashed and with a cold cache, then the coordinators will route majority of reads to other replicas which have a hot cache, so that you're not impacted as much by this event.
Yeah, very good. Thanks, Tomek. Question from Chandra. Is anybody using ScyllaDB for user session management that you know of? Yes, there are. One specific user that's using ScyllaDB for session management is Medium, for example. All right. Yeah. And there are others, but I'm not sure if I can mention them. Let's see which other questions we have. We are almost getting there. Very good question. I am a bit confused. Is ScyllaDB a cache or is ScyllaDB a persistent database? So ScyllaDB is a persistent database with its own cache implementation. I mean, sorry if it wasn't clear for the presentation, but we are a database, we persist your data, but we also implement a cache. And our cache is pretty much just as performing as other in-memory types of databases. Thank you very much for your question, by the way, Thomas. Sorry if we confused you somehow. Is the cache content sharded between nodes? Do you use consistent hashing? Yeah, I think it's a good question. Can you elaborate a bit on how the cache gets distributed per shard? How it gets essentially divided per vCPU?
Yes, so we use the hash function to distribute keys between the nodes, like Cassandra. And we also use the same hash to distribute keys between CPUs, but in a different way. Won't get into the details, but the token is used to distribute keys between shards as well. And as I mentioned on the presentation, the cache lives on the CPU, which also is responsible for the data. So it lives on the same CPU, which manages SS tables and mem tables for that key.
Very good. Thanks, Tomek. Is caching an enterprise feature only? No. ScyllaDB's cache is available in ScyllaDB open source. And we are almost up of time, guys, so I will select just one more question. And then, unfortunately, we have to say goodbye, but don't worry. We are going to follow up with you via email in case we haven't addressed your question. So last question, Tomek. Can you elaborate on how ScyllaDB handles caching validation? Is it TTL based on the cache, or are the cache entries kept up to date as the data changes?
Yeah, so I think I already answered that, but the answer is that we use LRU, and TTL is handled by removing objects during read when they are read. Or they can also be evicted by LRU before they are read. That's also possible.
Perfect. So, Tomek, thank you very much. And again, guys, if you didn't answer your question, don't worry. We are going to get in touch back with you, me and Tomek. So we will ensure your question gets answered. All right. So expect an email from us. And guys, thank you very much for being here today, Tomek. I hope you have a very good rest of your day. Thank you very much for doing this. All right.
My pleasure. Thanks.